Hi, and welcome to this quick look at the origins of reaction order. We're going to be using the rate determining step idea to explain where reaction order comes from. So first of all, let's clarify what is the order of reaction. It's the power to which the concentration in the rate equation is raised with respect to a certain reactant. So you might have a reaction between A, B, and C. So what this means is the rate equation is in moles per decimeter to the -3, second to the -1. So the units of rate are put in on the left-hand side. The individual concentrations of the reactants in the rate equation are in moles per decimeter cubed. But rate constant units might actually vary, or it might have no units at all. So calculating the rate constant is actually beyond the remit of this particular clip. I'm not going to be going through the initial rates method for calculating reaction order either. I'm just going to discuss how the rate equation is connected to the order of reaction with respect to a certain reactant. So let's take a typical example that we've come across before. So this is from the first year of OCR Chemistry A, and it's obviously a nucleophilic substitution. It could also be considered to take place in two steps. So step one is the breaking of the carbon-chlorine bond. This is an endothermic process. It takes energy. And then step two is the hydroxide ion combines with the cation that's produced. So obviously if that chlorine comes off and both electrons move onto it to form a Cl- ion over here, you have a CH3 plus left behind, which is what I'm putting in here. And then very quickly that finds and combines with the OH- ion. They attract one another and you get your product, which is the methanol molecule here. So the slow step involves breaking bonds, and then the fast step will involve making bonds as a general rule. So because you're actually breaking this bond, this is the slow step. This has to happen first. So in order to create the overall equation, you'd obviously have to cancel out all the CH3 pluses because they don't appear in the overall equation. So therefore, the slow step must control the overall rate of reaction, as CH3 plus has to be made before the fast step can start. So in other words, this cation has to be generated before it can go and react with the OH- in the second step. So there's only one species whose concentration controls the overall rate of reaction, and that will be CH3Cl. So the rate equation for this particular reaction is rate equals K times the concentration of CH3Cl raised to the power of 1. So you can see there's no number written in there, so mathematically that means this term here is raised to the power of 1. So because there's only 1 mole in the slow step, you can see that here, you can assume that it's first order with respect to CH3Cl in the rate equation below. If it happened to be 2 moles, then it would be second order, and you put a little 2 in superscript next to this. So the power would be 2. At the moment, the power that's being raised to is 1. All the other species in the fast step we saw a moment ago are 0 order because they have no effect on the overall rate. It's the creation of this species here by the breakdown of this bond here in this molecule, which is actually controlling how quickly this reaction goes. So let's have a look at a typical multiple choice exam question. So they're proposing a mechanism for this reaction, and obviously we're only interested in the slow step because that's for constructing the rate equation, because they wanted to choose an appropriate answer for the rate equation. So if you look in the slow step, you have 2 moles of NO2 gas in the reactant side. So therefore, the rate equation you're going to choose is rate equals K times the concentration of NO2 raised to the power of 2, because there's 2 moles of it in the slow step, which is the rate determining step for this overall reaction up here. So just checking the mark scheme, and we can see that the answer was indeed C. Okay, thanks for listening. Until next time, see you soon.